Now, before we look at the next idea of how we find this gradient function, I need to have a bit of a chat about limits, a bit more about limit theory and how we find the limits of functions, because I'm going to need that. There are different ways of finding limits. The simplest way is a direct substitution. Something like this. You've got this function x plus 7. You want to know what this function is approaching as the x value is approaching 5. Now, because it's a nice continuous function, it's no issue. We can just substitute straight in. So 5 plus 7 is 12. And if you think about it, you've got your straight line. Sure, as that x value is getting closer and closer to 5, well, it's sliding along the line, and so it's got to get closer and closer to the y value of 12. The second way of treating it is factorize and cancel. You see, if I've got something like that, I can't do a direct substitution, because I'll get that problem of 0 over 0. And what is 0 over 0? Some people say, oh, it must be 1. Anything on the top of itself is 1. Others will say, oh, it's got to be 0. 0 on the top of the fraction always gives you 0. And then there are others who say, oh, well, it's undefined because bottom of the fraction can't equal 0. So what is it? It's undefined, by the way. All right. So we factorize and cancel if possible. The top, of course, can do that. So we get x plus 3, x minus 3. We then can cancel the x minus 3s. And now I can do a direct substitution. And 3 plus 3 is 6. So we know if we were to draw this particular graph, what's it going to be? Well, essentially, it would be the straight line, x plus 3, but there would be a point discontinuity at 3. It wouldn't exist there. So as it's approaching 3, yeah, the y value would be approaching 6. So that's the idea of factorize and cancel. Then we get these third ones. And we need a very special limit in order to do it. And it's all to do with our hyperbola. What is happening as x is approaching infinity? You see, you can't just substitute infinity into a function. It's not like other numbers. It doesn't work like that. So we have to use limits when we're dealing with infinity. Well, we can see from our graph, and when we know what the hyperbola looks like, that as those x values are getting bigger and bigger and bigger and bigger, then that curve is getting closer and closer to the x-axis. So the y value must be getting closer and closer to 0. So therefore this limit must be true. Now using this allows us to investigate something like this. So the limit as x approaches infinity of x cubed plus 3x squared plus 2x minus 1 over 4x cubed minus 1. So something like that. What we do is we divide everything by the highest power. The highest power there is x cubed. Now why do that? Well, we've got a lot of cancelling that now happens. The x cubed on the x cubed becomes 1, of course, but then we get 3 on x, 2 on x squared, and so on. But now I can go back to that limit. Sure, our special limit was 1 on x, but it could have just as easily been 1 on x squared, 1 on x cubed, whatever. Whenever you got constant over infinity, if you want to think of it that way, then you know that's approaching 0. So all of those fractions we now know are approaching 0, and we're just left with constants, 1 on 4. So that limit must be a quarter. But what this now allows us to do is to not actually do that working out. Because effectively, if that's the technique we're going to use every single time, then clearly when we're dividing by that highest power, the only thing I'm ever going to be left with is the coefficient of the terms with the highest power. Because they will always cancel, x cubed over x cubed in this case. So that's all I need to look for. So if I see something like this, 4x minus x squared on x cubed plus 1, x cubed is the highest power. It's like saying everything else is going to disappear, because that's going to go to 0, but the one with the highest power, whatever its coefficient, that's what I'm going to be left with. So this one, I'd be left with 0 over 1, which is 0. So it must approach 0. This one here, the highest power is x to the power of 7. So I would be left with 1/3. Coefficient of x to the power of 7 over the coefficient of x to the power of 7. One like this, x cubed plus 2 on x squared minus 1. Well, that's an interesting one, because when I just look at the coefficients, I get 1 over 0. It's what we were saying. Well, when we see constant over 0, we think of infinity. Just like before I said, when we see constant over infinity, we think of 0. Well, you get the same the other way around. So if I see 1 over 0, It's undefined is more the correct term, but when I'm talking about limits, I'm saying, oh, well, this will be approaching infinity, or minus infinity if it happens to be, a negative. This then takes us back to curve sketching, and we saw questions like this. When we did it before, we did it via a polynomial division. Well, this gives us another way of doing it, because essentially what we were doing is finding the horizontal asymptote. Remember, the horizontal asymptote tells us what happens out at infinity. So if I investigate the limit, I can find out what happens out at infinity. So here, well, x squared is the highest coefficient, so I know 1 would be the horizontal asymptote, y equals 1. It's an alternative way. Obviously, polynomial division still works, but I put in the notes an exercise from the old Terry Lee book, exercise 6.1. For some reason, our textbook doesn't have an exercise on limits. I think it's a worthwhile thing to look at.